Silver chloride is not a very soluble substance, but if you do put silver chloride in some water, a tiny, tiny little bit will dissociate into silver ions and chloride anions. And in fact, we might even could draw this equilibrium like this, where only a tiny little fraction breaks apart into ions. And since a very, very tiny amount does dissolve, we can write an equilibrium expression for it, where we take the concentration of the product of that, over the concentration of the reactants. That's a solid, so that makes no sense whatsoever. This is a solid. It has no concentration. So with that removed, there is no denominator on this, and we simply have our solubility product constant as the concentration of the silver ions in solution times the concentration of the chloride ions in solution. Now, we could look this info up in a table, and we would actually find that the KSP for silver chloride has this value of 1.6 times 10 to the negative 10. That's a very small number. This information is known for the insoluble or slightly soluble materials and is usually found tabulized. For you doing end of chapter practice problems, you would want to use Appendix J in your OpenStax textbook, and I'll be posting a link in our resources directly to that, and you can use that. If you were taking the AP exam, it would probably information be given to you in the beginning of the problem, where they often give tabularized information that's not a complete list, but things that are or might be relative to solving that particular problem. One type of problem we often see with this is when you are asked to find the solubility product constant for a material from the molar solubility for that. Now, if you remember when you studied solubility back in high school chemistry, you often had data that might look like some kind of curve where your independent variable was temperature and your dependent variable was grams of solute per some amount of solution or solvent. Sometimes this was 100 grams or 100 milliliters, and you created a graph that gave you the molar solubility of a saturated solution equivalent along your best fit curve. So sometimes that information is provided for you. Let's do an example with silver bromide. If this solubility curve was for silver bromide, we might read it at 25 degrees Celsius on the independent axis to find that the variable gives us a 1.3 times 10 to the negative 4th grams of silver bromide dissolved in 1 liter of water. That's not molar solubility. That's in grams per liter. We need to change grams to moles. So we take our given solubility at 25 degrees of 1.3 times 10 to the negative 4th grams of silver bromide per 1 liter of water. And we need to change that to moles. And we know that 1 mole of silver bromide weighs something about 187.8 grams is the molar mass. Now, that's going to give us our answer in moles of sodium bromide. And when we set this up, that's moles of silver bromide, we can write our KSP as the concentration of the silver ion times the concentration of the bromide ion. And this is what we're looking for, our KSP. From this, we know that our concentration of silver bromide, but we need to know the concentration of the individual ions. So pulling from the mole ratio from our equation where AgBr dissociates into silver ions and bromide ions, we know that it's a 1-to-1 ratio between them all. So in our mole ratio, every time we have 1 mole of silver bromide, we're going to get 1 mole of silver ion. And because it's a 1-to-1 ratio between the silver and the bromide ion, it works for whatever our answer is, will be our answer for our bromide ion too. So punching that in a calculator, we find it. We get 6.7 times 10 to the negative 7, and our unit would be, well, we've removed the grams of silver bromide, and we're left with moles of silver bromide. We've removed moles of silver bromide and made this moles of silver ion, and 6.9 times 10 to the negative 7 moles per liter of solution of the bromide anion. Now, we can use these two values to find our KSP. So 6.9 times 10 to the negative 7 moles per liter for the silver ion, and the same number for the bromide ion. And this gives me a KSP value of 4.8 times 10 to the negative 13. That's a very tiny number, and the silver bromide is very insoluble. I know this because my solubility product constant is a very small number. Here's the whole thing. Let me know if you have any questions or concerns. Thank you very much.